Let me first thank Roland and the committee. It's a real honor to be here. We've all learned so much from the Scandinavian School of Theoretical Chemistry, and it's a real honor to try to give something back, so I hope you enjoy. The talk is the same talk I was going to give. I called it Phase Space Hamiltonians and VCD, but really this will be about chiral induced spin selectivity and electron transfer. It's all the same in my mind. And before I begin, I'll always forget to thank people, so I better thank them now. A lot of people have contributed to the work I'm going to be telling you about today. In particular, the work today on VCD was done by Titouan Dastan, and a lot of the fundamental work of phase space that I'm going to tell you about was done by these gentlemen, Janze, Tian, and Shwezi, and Coraline. She's really been at the heart of all of this. And I'm not sure I'll get to talk to you about magnetic field stuff, but if I do, that's the work of Monsi, and I've had some wonderful collaborators over the years. Robert and Jonathan also deserve a lot of credit. And Nadine's work with Yihan and Zheng will also be discussed a little bit, time permitting. Okay, so here we go. Before I begin, I got to say just a couple words about chiral induced spin selectivity. The chiral induced spin selectivity effect is not always well known outside of experimental worlds, and I've been the last 4 days in Germany just talking about it nonstop. But it's probably, I should assume that nobody knows much about it, so let me just say a couple words about this. These are the experiments that first revealed there was something really deep going on and that was measurable. And the experiment goes like this. If you take a layer of gold, okay, and you shine light on it, and the light could be polarized linearly or counterclockwise or clockwise. If it's gold, it's very well known that because when you come in with circularly polarized light, you have to excite electrons, which have a matching orbital angular momentum. And if you have gold, you have strong spin-orbit coupling, which means that that orbital angular momentum will be coupled to spin, and therefore it's to be expected that the spin, when it comes out, will have a different spin polarization depending on whether or not you come in with clockwise, counterclockwise, or zero, or linearly polarized light. What's amazing is that if you take that gold layer and you cover it with a self-assembled monolayer of DNA, and you do the same experiment, now when electrons bounce out and you measure them, they all have the same spin. They're all negatively spin polarized. So DNA seems to be acting like a spin filter in a sense. Only one form of electrons can get through it with a given spin. And nobody understands why. Okay, I was just at a conference for 4 days and there were, let's say, 5 different explanations, and nobody even's really, and the calculations are hard enough. It's really a mess, okay? But the experiments are actually clear enough that something is going on. And what is also clear is that it's not the most obvious thing. Because if you were to say to yourself, well, look, it's DNA. DNA is a helix, right? Then you would say DNA is a helix. As an electron moves through like this, it makes a magnetic field. It must interact with its own magnetic field, and that magnetic field is then enough to give you a spin preference. But if you do the math, and this is what Nitzan and Gersten did a long time ago, you would need on the order, with reasonable parameters for DNA, you would need on the order of 10,000 turns of the DNA to get a measurable effect, whereas they see a measurable effect in 4 turns. Okay, so that's not what's going on. I won't actually say too much about this because for time being. Let me just say this. There's also a question about whether or not the effect is largest because of the spin-orbit coupling of the metal. That's also an open question, but there are clearly examples where that's not true. You can find the same thing on gold, which has a huge spin-orbit coupling because it's heavy, and copper. So, 11%, 15%, whatever. And finally, what should really blow your mind is that DNA and polyalanine are both going to be right-handed helices. And when you do the measurements, you find that for DNA, the electron comes through with spin down, and for the peptide, it comes through with spin up. So it's really not just how it moves around. There's something much more fundamental going on, and nobody understands what that really is. One word about why we care, right? You might say, like, who cares about the spin? Actually, some of the most interesting experiments that have happened in this regard have to do with water oxidation. When you take water and you split it, and you form H2 and O2, a common side effect is actually you make peroxide, H2O2. And the idea is that you make OH radicals in the meanwhile, and the OH radicals recombine on a surface and they make H2O2. And what's interesting about that is that if the OH radicals were both spin paired up, then they couldn't recombine to form H2O2 because they'd be a triplet state. And actually that's what's seen. If you cover the catalysts with chiral molecules, you actually reduce the amount of H2O2 on the surface, and the efficiency of the water splitting process is larger. So everybody cares about this, but nobody knows why. Nobody knows what's going on. And actually, one of the most interesting things is that one of the people who's trying in a very abstract way to do this is actually at this university, Jonas Franzen, in physics. Okay, so nobody knows what's going on. I have to give 4 review slides now of just basic theory before I tell you my take on what's happening. Okay? So what is the energy of a hydrogen atom? My God, we all know this. This is the energy of a hydrogen atom. It's a 1s orbital in its ground state, and the energy looks like minus mu times this, where mu is the reduced mass of a hydrogen. This is where we start the analysis. Okay, everybody understands this, but everybody also knows that in class, you always forget about this reduced mass part. If there's one thing I'm going to tell you about today, it's my God, you better remember this reduced mass. Okay, and we'll see why. Now, where does that reduced mass come from? Let me just remind you of your basics, right? Normally, this is the hydrogen Hamiltonian, the kinetic energy of the nucleus, the kinetic energy of the electrons, and their attraction. Now, the Born-Oppenheimer approximation says I'll freeze the nucleus and I just work with everything else. So this becomes a C number instead of an operator, the kinetic energy of the nucleus. And if you diagonalize that operator, you get a mass here, the mass of an electron, not the reduced mass, but the total mass. But if I first switch variables, right, to the center of mass and the relative coordinate, then I get the reduced mass. Okay, I think everybody understands that. You cover it always in your first year of chemistry, but then you forget it when you're 40, okay? All right, now one more thing about the Born-Oppenheimer approximation, right? The Born-Oppenheimer approximation, we all know what it means. It says that, you have this nuclear kinetic energy and the rest of it, and you diagonalize the rest of it, which is called the electronic Hamiltonian. And when you diagonalize it, the most obvious thing is just remember, your molecular orbitals that you get when you pull this out, they depend on the position of the nuclei, right? Not on the momentum. That's a key fact, all right? Then if you take these orbitals, or these eigenstates that you make, just imagine you could make them. Imagine, I give you a full CI, like was talked about earlier, and you put the total Hamiltonian back in the basis of that, this needs to say the full Hamiltonian. The full Hamiltonian, the basis of these electronic states, you get basically this, which we all know. The new terms that arise are the so-called derivative coupling terms, or in physics they call them the Berry connection terms, okay? These are the things that everybody wants to focus on. And it's sad that last week David Yarkoni died. It's terrible news. He was really the person who probably knew the most about derivative couplings in the world, I would say. And I remember him having a great line with me. He said something like, "Did you think they would be clean? All the problems are hiding in there. They're a horror, okay?" And the horror of this is that everybody sees what they want to see. So if you're a physicist, you'll look at this and you'll say, it's a matrix, right? Let's focus on the diagonal parts. There can be diagonal parts sometimes. In fact, there will be. If you have magnetic fields around, if you have spin-over coupling, there are diagonal parts. But the chemist doesn't give a damn. The chemist almost always looks at this and says, I will focus just on the off-diagonal parts that give me transitions, okay? But they're all in there. The derivative coupling is a beast. And in some ways, that's what we have to deal with today. Okay. So the first thing I want to tell you is that electron transfer has a conceptual momentum problem. And what do I mean by that? Well, Leif and I go to a Gordon conference every couple years, and it's just about electron transfer, the whole damn thing. And the whole damn thing can be summed up in just a few slides, okay? The slides that Marcus told us years ago. So think about a system where you have iron 2 and iron 3. Two irons and a +5 charge. If the water goes one way, we all know that at that geometry, the ground state should be +2 on the left and +3 on the right. And if the water goes the other way, it should be +3 on the left and +2 on the right. And in the middle, somehow, by symmetry, it must be a +2.5, +2.5 ground state. Okay, everybody knows this. And everybody knows that there's a curve crossing problem, a Born-Oppenheimer curve crossing problem that tells you what electron transfer is. Everybody knows this, okay? What does it look like? It just means the fact that if the water spins slowly, right? If the water turns slowly, and the system moves. This is a nuclear coordinate here. If the water turns slowly, an electron will move from side to side. But if the water turns fast, right, then there's simply no time for an electron to move. That's the physics that Marcus tells you about. And as a result, the only conclusion from that is that you have a curve crossing, right? That the curve crossing is such that the ground state, if the water molecule is arranged this way, has electron on the left and no electron on the right, so it's 2, 3. But there's an excited state which is 3, 2. Okay, this is not so. I think everybody in this room. This is a molecular chemistry meeting. Chances are everybody knows this, and what that means is that when the molecule spins fast, it actually goes like this. It jumps surfaces. Okay, so the idea is that, right, the electronic dynamics are tied to the nuclear motion, and if the nuclear motion is slow, you stay on the lower adiabat, so you have an electron transfer. If the nuclear motion is fast, the electron doesn't have time, it means you must be going up a surface and jumping surfaces. Okay, so that means there are two ways that you can get electron transfer, okay? The two ways are you can go over a surface on the lower surface, or you can jump up to the higher surface and rattle around and come down. Adiabatic and non-adiabatic electron transfer, okay? Everybody knows that, at least at this Gordon conference that Leif and I go to. All right? Everybody knows this. And that's all about the diagonal part of the derivative coupling. That's what it is. It tells you when you want to hop and when you don't want to hop. Okay. There is, however, another part, an on-diagonal part of the derivative coupling that Marcus never considered. Okay? And it's actually crucial, I'm going to argue, over the next 30 minutes. What is it that makes it so interesting? Well, here's the thing, right? Let's suppose you imagine, right, that you're running an MD simulation. Your energy in that MD simulation is translationally invariant. I move the molecule from here to here, same energy. I rotate the molecule, also, same energy. Okay, that means that as the molecule moves and vibrates, right, the nuclear momentum is going to be conserved. That's what it comes from, translational invariance. Okay. But now you have a problem, because if I run along this ground state, right, I'm conserving the nuclear momentum. I might say that's a good thing, but it's not a good thing, right? It's not a good thing because what about the electron? The electron is moving from side to side. If the electron moves, okay, and the nuclei are moving, the total momentum should be conserved, not just the nuclear momentum. But that's not what you're getting when you run Born-Oppenheimer dynamics. When you run Born-Oppenheimer dynamics, sure as hell looks like you're conserving the wrong thing. Okay? And in fact, that's a problem. It's a real problem. Now, why is it a really interesting problem? It's an interesting problem because there must be conservation of momentum, linear and angular. And as far as linear momentum goes, there are only two forms, nuclei and electrons. That's all it could possibly be. However, with angular momentum, there's now something new, right? There's spin. And now you've got a funny question to ask yourself, right? Because what this means is that it's very possible that when electrons move from one side to another side, just to maintain angular momentum conservation, there's going to be a spin preference, where maybe a upspin goes more easily than a downspin. Because what you know is that there could be all sorts of spin changes. No matter what's going on there, we must maintain angular momentum conservation. There's a real issue with Marcus theory and a lot of quantum chemistry because these states, in a sense, are degenerate. You've got two spins for the donor, two spins for the acceptor. It's a four-state problem, not a two-state problem. It's not a classic Marcus problem. But this is how life is. And that's why it's exciting. All right? So that's what we want to get across. How are we going to try to understand this? That's what I want to tell you about. One way of doing this, and it's potentially an explanation for what's going on, and I think it probably explains a lot more, to be honest with you. And I'd be happy to talk. Some of us are going. Well, anyway, after the talks, if we have time, I'm happy to talk to any student as well who wants something off the record. Okay. So how do you get around this? The thing is, you're stuck with the Born-Oppenheimer approximation. Everybody's stuck with it. I mean, even in your own head, you know. We're like the dinosaurs nowadays, as far as I can tell. We are the people who were brought up not to believe in plate tectonics, and we have to make sure that we don't die as the people who don't believe in plate tectonics. Okay? And new generations will come and have new ideas. Here's one approach, okay? I call it a phase space approach. Now, the big problem with Born-Oppenheimer is electronic momentum. It's just not in there, okay? It's not in there. And You might say, well, what is the motion, what is the momentum of an electron along a Born-Oppenheimer eigenstate? So I'm moving along, what's my momentum? Well, the answer is obviously 0, right? Because adiabatic wave functions are the wave functions that diagonalize the electronic Hamiltonian. They're real. I mean, for the most part, they're real, unless I've, without spin, let's at least say that for sure they're real, and their momentum is going to be 0. Real wave functions have 0 momentum. But of course, that's not right. Just take a hydrogen atom. You take a hydrogen atom, and the atom is moving with velocity v, the electronic momentum had better be the mass of the electron times v. Okay? That's the right answer. Born-Oppenheimer gives you the wrong answer. It gives you 0. In fact, more generally, right? Suppose that you had a simulation which was moving around, okay, in time. As the nuclei move, you will have a change in the average electronic position. And in fact, the average momentum should be that. We all know that should be true. That's basic quantum mechanics. But it isn't within Born-Oppenheimer. So now you come to one of these funny things, right? When you try to write articles, review articles, or any kind of article, you always get somebody who criticizes you. Born-Oppenheimer conserves momentum. And you're like, yeah, it does conserve momentum because it sets the electronic momentum to 0. That's not really conservation. I mean, it is and it isn't, okay? All right, we need some new theory. So what's that theory going to look like? Okay, so now we're going to come back to the hydrogen atom, right? The very basic hydrogen atom. What are we going to do? So remember, if I switch variables to the relative position in the center of mass, I do get the correct electronic energy for the hydrogen atom, and I also get a non-zero electronic momentum because I'm entangling the nuclear and the electronic motion, which is correct. That electron follows that nucleus. Its center of mass motion does that. Okay, so then you say, and my collaborator first said to me, well, what's the problem? Let's just take 2 center of masses and be done with it. But that's a dumb idea in the end also, okay? Why is it dumb? It's dumb because if I had one hydrogen atom here on Earth and one on the moon, putting in, 1 center of mass certainly doesn't help, right? I mean, that would be really insane. That would break all the rules of quantum chemistry. Size consistency would go out the window, right? We cannot do that, okay? But to put in 2 centers of mass, what happens when the 2 atoms come together and they form a bond? What if I have a solid? This problem does not go away just by looking at 1 center of mass and trying to do it. In effect, we have many centers of masses, but we got to be careful about how we do it. Okay, so we need a trick. And here's what I'm going to tell you is my trick, okay? My trick's going to look like this. If I take the hydrogen atom in a diabatic basis, that's my true Hamiltonian, okay? Now I go to the adiabatic representation, meaning that I diagonalize this operator. It really doesn't even depend on, whatever. It barely depends on the nuclear position, but whatever. I diagonalize it, fixing the nuclei, right? When I do that, I have to conjugate the Hamiltonian, and what I get is I get the the kinetic energy of the nucleus, a diagonal basis of electronic eigenenergies, and I get all the non-Born-Oppenheimer stuff that I usually throw out in the Born-Oppenheimer approximation. Now I take the classical limit of this. So now I make these kinetic energy operators and these positions C numbers, just variables. And that's my new Hamiltonian. And then I go back to the diabatic representation. I transform back. If this was U and U dagger, I make it U dagger and U. And now I get something that looks like the original Hamiltonian, only this is no longer an operator. Okay, it's just a C number. And I get these corrections over here. And if I rewrite all that, it looks like this in the end. It looks like the kinetic energy of a nucleus, but now you see what's happened is I've changed the meaning. That kinetic energy now is no longer the kinetic energy of the nucleus, it's actually the kinetic energy of the whole system. In a sense, I've transformed something away here. And this operator, in fact, if you diagonalize it, it gives you exactly the correct energies and the non-zero momentum. This is an exact transformation, actually, of the problem. It turns out you're not supposed to just diagonalize the electronic Hamiltonian. You have a term up here that you're supposed to include also, which actually couples the nuclear motion to the electronic motion. It's a non-Born-Oppenheimer term. Now, just to be clear, what's going on, right? If I do this is the hydrogen atom. My ground state, if the atom is not moving, will still be a 1s orbital. I didn't change the laws of quantum mechanics. But if the orbital is moving, surprise, surprise, it's going to look like a 1s orbital and a little bit of a p, because it's telling you the electron is moving with the nucleus. How else could it be, right? That's how it's got to be. Now, the experts in the room who know all about the the Born-Oppenheimer approximation say, well, that's sort of obvious, right? Well, maybe not quite obvious. Let's put it like this. Not yet obvious. We're going to get to the obvious part in a minute here. If this is what I'll tell you is this: if the hydrogen atom, and if it ends up being the case that I have a coupling between the electronic momentum and the nuclear momentum, and I'm supposed to diagonalize this operator, which I'm calling a phase space operator, because it depends on it's an electronic operator, right? Only the electrons have hats on them, but it depends on the nuclear position and the nuclear momentum. Well, if this is what it looks like for one electron, the idea is that for many electrons, it would look like this, where every single atom has a little electronic operator, has an electronic operator attached to it. And here, for one atom, I needed the electronic momentum. So this operator gamma, you would think of it as the local momentum around atom A. That's what has to be in there. The idea is that every atom, when it moves, it sort of drags the electrons around it. So how do you choose this operator? Okay. So this is where some of the experts in the room will know what's going on. If you look at the adiabatic electronic states that you get, right? Suppose until now, right, everybody, if this is the first time I'm telling you about a phase space electronic state, then yesterday you knew all about adiabatic states. And adiabatic states, the whole idea is that you parameterize the electrons relative to the nuclear positions. That's all that this says. If you move an electron and you move the nuclei, then every adiabatic state should be invariant. And then if you sandwich this between state 2 and state 1, what this tells you is that the electronic momentum plus the sum over all the atoms of the derivative coupling must equal 0. It's a sort of obvious sum rule. So again, this is the electronic momentum, and this looks like, this D then looks like it better be the local electronic momentum around atom B. Okay, now what does that mean, the local electronic momentum around atom B? Okay, local derivative couplings are sometimes called, to a certain extent, electron translation factors. And in 2012, I published a paper, which I take full responsibility for now, okay, saying that we should remove them from derivative couplings in the context of surface hopping. This actually was a result that helped me get tenure, okay? It helped me get tenure because at the time people were very interested, why was surface hopping not maintaining momentum conservation? And I thought, oh, well, I figured out it had something to do with this. Yeah, but that was actually wrong. Not only was it wrong, Roland actually listened to me, right? Look what he wrote here in one of his papers. I apologize, Roland. He said he actually believed what I said. He said, this lack of invariance can lead to unphysical results and is due to the absence of electron momentum. So I sort of got it right there. He said, I've addressed this problem by including this, which results in a simple recipe to restore translational invariance. So I convinced myself, I convinced Roland, and now I'm convincing you. Boy, did I get it wrong. It was my fault. Okay, it was wrong because at the time I thought this was a problem of the way I was doing the calculation. What was really the problem, right? You're not, that local derivative coupling that I knew was there 10 years ago, you're not supposed to take it out. Instead, you're supposed to put it right back in. You're supposed to turn that into a momentum coupling in the Schrodinger equation. And if you do that, you're going to see later on in maybe 10 minutes that you get nice properties out that you were not expecting to get out. Okay, so I'm telling you now that, let me go back for 1 second here. This is what the hydrogen atom is supposed to look like. This is what I'm going to build now. My new Hamiltonian that I'm going to diagonalize is going to be a function of the nuclear position and the nuclear momentum. And when I do such a thing, I need to have these couplings, and I'm going to build these couplings in two different ways. I'm going to build them from two terms. One I'm going to call gamma A prime, and one I'm going to call gamma A double prime. What is this gamma A prime term? So the gamma A prime term literally just looks like the local electronic momentum. Formally, I'm going to write it like this. Here's electronic momentum. I'm going to multiply it, and I'm going to multiply it by what I'm going to call a theta function, which is really just a partition of overall space of unity. So basically, this just says, if you're near this hydrogen over here, this function should be 1, elsewhere it should be 0, and it should decay exponentially. So just trying to carve up space. And if I do it and I put it on both sides of the momentum operator, this is now a Hermitian operator. And if I sum over all of these over all atoms of theta A, I'm just going to get 1. So if I do that to this term here, I do get the sum relation that I wanted, that the sum over all these new, you can call them electron-phonon couplings, you call them whatever you want to call them, actually is the momentum. And it does depend. You might say if you're a purist in the room, the Scandinavians never like parameters, okay? I do have a parameter here. The parameter I have is that I'm stuck with these sort of sigma A and sigma B operators. I'm stuck with the idea that I have to say how much it is that every electron near this atom stays here. You know, like if I have two atoms, right, I'm trying to divide up the electrons on one versus the electrons on the other, and I have to know sort of roughly a van der Waals radius. I'm stuck with that parameter. I can't get away from it. That being said, I'm going to show you here, these parameters are it's pretty invariant to these parameters. And here I'm showing you what is the ratio of the electronic momentum to the mass times the change in velocity. It's not always 1 exactly, and there's actually good reasons it won't be 1, but it's always in the right direction as long as the parameter is small enough. And it can be as high as 2, as low as 0.5, but it's not bad. It's better than nothing. You got nothing with Born-Oppenheimer, okay? Now, one more thing I got to tell you. There's also going to be one other term here, which is going to be a local, what we call, instead of electron translation factors, local electron rotation factors. I won't say much about this except to say that, to some extent, these are like the spin Coriolis forces that are already used in magnetism. But there's not just a spin part, there's an orbital angular momentum part too. And they will obey everything you want them. Okay, so what are you going to get from this? I'm telling you, in my mind, it's becoming more and more clear that quantum chemistry should not be diagonalizing Born-Oppenheimer surfaces. We should be using phase space surfaces. They're Hermitian, okay? They are complex, but they still have real eigenvalues. You get non-zero electronic momentum. You can show momentum is conserved. In fact, you can even show roughly get a continuity equation of where the electrons are. And more than anything, I'm going to give you now 2 experimental things that should be validatable, okay? One, I'm going to show you VCD spectra, which is not something that's too commonly talked about in quantum chemistry, because it's like the bad child in the corner, and vibrational energies. Okay, so this is the part 2, the conclusion of part 2 of my talk. Okay, existing quantum chemistry packages are based on the Born-Oppenheimer approximation, where you freeze the nuclei and diagonalize the electronic Hamiltonian. But there's a new paradigm, I think, which is a much better one, which is to diagonalize a phase space Hamiltonian, which is parameterized by both r and p. So your orbitals will now depend on velocity of the nuclei. You will conserve momentum meaningfully. Now I'm also to blame for something else. I've been telling people for the last few years that we needed to worry about the Berry curvature, that the Berry curvature had all this in it. And the Berry curvature, for those of you who know what it is, it's like the derivative of the derivative couplings. And you can show it's been very, very helpful in certain problems in condensed matter. I'm now going to tell you I no longer really believe in doing it in a certain sense. And the reason is the Berry curvature is a way to fix up the Born-Oppenheimer approximation. And I'm telling you, I think that basically we can't go post-Born-Oppenheimer. We really need to go pre-Born-Oppenheimer in a sense. We've got to do it in a totally different context. And if we do, I think we can basically avoid most of the problems that arise with calculating the expensive Berry curvature. That's my ansatz now. Okay, now let's say, how do I justify any of this? Besides the fact that I get a non-zero electronic momentum, how do I experimentally show this is actually correct? Okay, you got to have some way you can show this. So what am I going to do? I want to talk about vibrational circular dichroism. So circular dichroism comes in many flavors, the 2 most common being UV-vis, right, electronic, or vibrational, okay, which is in the IR. Now, ECD, for electronic, people pretty much know how that works, but VCD is always a little bit more complicated. Why is it complicated? Well, you see, the CD strength is given by the rotatory strength, which looks like this. If you average over all directions, right? So what does it mean, CD strength? So you have your molecule here, which is chiral, and you come in with light. And the light can be right-handed or it can be left-handed, and you'll just look at the difference in absorption. And you average over all directions in space. And when you do that, you get the rotatory strength is the factor that emerges. Now, this rotatory strength is the dot product of the electric dipole between states 0 and 1 and the magnetic dipole between states 0 and 1. And each of these has an electronic and magnetic dipoles both have electronic and nuclear contributions. And both of these components are crucial for accuracy. So the nuclear part is trivial, right? It's like, they're like sticks. I know where the nuclei are, but the electrons are more complicated. But you need both, because if you were to look at the contributions from both, you'll find that they almost entirely cancel with each other. That's why VCD is so sensitive. Because, because it's got 2 big terms that are actually canceling. Now, by the way, one interesting thing is that VCD is so sensitive to chirality that it actually is used nowadays as a substitute for crystallization in drugs. The FDA in America was always very nervous about chirality after thalidomide. And for a long time, to prove you had the right enantiomer, you had to actually get a crystal of your drug. But now, because they realize VCD, every single normal mode of a molecule actually has a very particular spectrum. It'll be plus or minus, and if you get them all right, it's you're pretty sure it's the right enantiomer. Okay. All right, now what's the problem? So the problem is what's the easy part? VCD has an electric part and a magnetic part. The electric part is trivial. The electric part, you just need the electric moment, the electric dipole between the ground electronic state and zero vibrational state, and the ground excited state and first vibrational state. And to get around this, you just expand the electric part in terms of the nuclear position. You can plug it in, and it works well, no problem. Okay, but there is a problem for the magnetic part, right? The magnetic part has a huge problem because formally, this electric magnetic dipole moment between the ground state and the zero vibrational state and the ground state and the first vibrational state is zero, right? It has to be zero because this is the magnetic moment, which is basically like the angular momentum, the electronic angular momentum. But the electronic angular momentum and the linear momentum, they're all zero between G and G. We just talked about that. In the ground state, the electronic angular momentum must be zero. So there is no term, right? VCD cannot be handled through Born-Oppenheimer theory in any simple way. Now, there is a way. People are smart, right? People realized this was a problem, and so Stevens and Nafi, they realized in different times, but really this part with Stevens, they realized that what you had to say was, well, when the molecule vibrates, it actually changes the electronic angular momentum according to this kind of an analysis. It's a double perturbation theory, where you look at the overlap of the ground state wave function response to magnetic field and the ground state wave function response to nuclear position. But a good theorist should be bothered by this because this is a linear spectroscopy, right? No linear spectroscopy requires a double perturbation theory. So why does this one, right? It's a conundrum, and it should bother you, and it bothers me, and it bothered me. And so here's the thing: if you believe that you can parameterize electronic states not just by nuclear position but by nuclear momentum, then you can actually calculate dipole moments and magnetic dipole moments that depend on R and P, and therefore you can take these derivatives and you can make directly VCD predictions, and so we did. Is that no longer working? There we go. Okay, so there we go. Here's the standard molecule everybody works on, oxyrane, okay? Oxyrane, you deuterate some, you have some hydrogens on here. It's the standard molecule, and you have vibrational modes that go from 673 wave numbers up to 3,000. And you can look at the rotatory strength, and these are the signatures, right? Now, the experimental data here was taken in solvent, okay? One of the reasons that VCD is so amazing is that the calculations here are done in gas phase, right? But nobody cares because when you're subtracting out the right-handed versus the left-handed light, a lot of the solvent details go away. You can focus just on the electronic properties you've got. And what you can see is that compared to experiment, the black, right? Almost always you're right? And the purple curve here would be what Stevens did a while ago, and the red curve, we did, this is a figure where we showed all sorts of different basis set dependence to show. The first time we did this, we had a lot of basis set dependence. Now we do this the right way. There's no basis set there's some basis set dependence, but it's very weak. And you can show that it converges. By the way, Roland might like this. You see this curve, this one here, V8? There's an article out there talking about how we get this wrong, right? And there's a nice article out there talking about how this is actually electron-electron correlation. I didn't say about how I did any of these calculations yet. All of these calculations are just generalized Hartree-Fock. That's it. The question of what happens when you put electron correlation in a phase-space context is a fabulous question. Why is it a fabulous question? It's a fabulous question because you're just going to say to yourself, what's this phase-space thing doing, right? Phase-space is telling you that I have to really worry about the connection when you have a nucleus, right? And an electron, and that electron needs to follow that nucleus as it moves just because it's tied by center of mass motion. Well, then think about it. What happens here? If I have an electron here and it sees this nucleus, what do? Well, then they're attracted to each other because electrons and nuclei are attracted to each other. But this nucleus, it carries an electron with it. So that means that the electron that goes with it actually sees this one goes with it, and there's now a slight net attraction between electrons. So you wonder, do phase-space Hamiltonians, if you put in correlation, allow for superconductivity, right? All sorts of interesting phenomena arise here that you got to think about. It's a different way of looking at things, and I think there's all sorts of interesting puzzles to be worked out here. Okay, let me tell you one more piece of evidence. I have like maybe, I think I have 3 minutes, something like this. One more piece of the puzzle here, vibrational energies. I'm going to tell you that phase space actually outperforms Born-Oppenheimer for phase space energies, for vibrational energies. How am I going to show this to you? I'm going to show this to you. So the problem is that the correction terms for real molecules are small, and we haven't actually worked. Our code is still very preliminary. We're doing this in QChem, and it's taking a long time. As you can imagine, we're trying to change the guts of the code. We're making the electronic structure now depend not just on the coordinates, but also on the masses and on the momenta of the nuclei. Okay, so and you can only do so much with the resources that you have. So it's going to be a model problem here. The model problem here is going to be a problem of 3 bodies, 2 heavy and 1 light. Okay, it's supposed to represent an O, an H, and an O. And this is a standard problem that people have used and all over the physics literature to try to understand proton transfer. And now we're going to compute the energy in 3 different ways. Okay, this is just a model problem with the attraction of this light particle to this heavy particle. Have these 2 particles repel each other, et cetera, et cetera. We'll do it with exact dynamics, with Born-Oppenheimer, and with a phase space approach. And we expect that Born-Oppenheimer should fail if we actually take the heavy particles and make them lighter. So this is going to be the mass ratio of the heavy to the light. And if it goes to 1, you can expect that Born-Oppenheimer will fail. You could say, how will phase space do, right? What should it do? Now, okay, these are the coordinates we use, the relative coordinates to the center, and et cetera. Okay, this is where the model comes from, and it's just an attractive potential. Now, I never show this slide here, but in this kind of an audience, I think you guys deserve to understand. What does it mean to take a vibrational energy here? Why didn't people do phase space stuff in the beginning? Why am I doing this now when we could have been doing this 100 years ago? Born-Oppenheimer is 1927. Really, people didn't want to do this because the idea is it's hard, right? At the beginning, you want to be able to build up a Hamiltonian from nothing but the positions of the nuclei. If you have positions and the momentum of the nuclei, they don't commute, so it has to be semi-classical. So you say, all right, I don't want to do that the real way. But if I do it semi-classically like I do, I claim you get better energies, but then how do you actually go from the electronic energies and then go back to a nuclear energy? You have to do a Weyl transform. So we did it, okay? It's there. You have to do it over the, you have to re-quantize a nuclear mode. Okay, anyway, we do it. So what do we get? Well, this is the mass ratio here between the heavy and the light particles. 3 means it's all base 10, right? So 3 means the heavy particles are 1,000 times heavier than the light particles, and over here they're 10 times heavier, okay? And over here, half, and over here they'd be like 1. And what you can see now is what's the error. So these are the energy gaps between the ground and the excited state for all these different methods: exact, Born-Oppenheimer, phase space, Born-Oppenheimer harmonic, phase space harmonic. And if you look over here, what you see is that the error, as the light particle gets heavier and heavier, the error of Born-Oppenheimer harmonic is the worst. Born-Oppenheimer normal explodes, but the phase space, especially if I don't make the harmonic phase space, it stays really low. As if to say, it's hiding there the whole time. Why in the world would we generate states why in the world would we generate electronic states not taking into account the momentum of the nucleus? Okay. So I think, so here we go, future work. What have we missed? It's not clear to me what we've missed. We might have missed an awful lot in quantum chemistry, right? You can show something very interesting. I didn't say it up here. If you run non-adiabatic dynamics with phase space surfaces, you can show that actually when you translate or rotate the whole system, you don't hop. That's not true for normal surface hopping. You do hop. You can show all sorts of things that are just really lots of fun. And more than anything, we should be able to, if we do this the right way, we're going to be getting out non-trivial spin polarizations. We should be able to say all sorts of questions about the spin during electron transfer and what happens. An obvious experimental question, right? This raises, right? Is vibrational circular dichroism how strong is it for systems where you see chiral induced spin selectivity? I mean, it raises all sorts of just very conceptually simple things that we should be asking. Perhaps for the theorist in the room, one of the most wonderful things is that StatMech, right? The whole field of study of molecular dynamics is all based on the idea of Born-Oppenheimer approximation, because you imagine that you have an equilibrium density matrix. This tells you that, in fact, the equilibrium density matrix if I go to higher order, is not even time reversible. So it's a real connection between dynamics and statistical mechanics and electronic structure. It really goes in all sorts of interesting directions. And the final thing I'll say is this. I don't have time to talk to you about how this works, but suppose you want to do dynamics in a magnetic field. Now, magnetic fields are super interesting for this kind of a question. Why? Okay, we all know how magnetic fields work. Charged particles are bent by magnetic fields. Okay, you have to be moving to feel the magnetic field. If you're not moving, you don't feel anything. Okay. Now, Born-Oppenheimer says what? Born-Oppenheimer, and so of course both nuclei and electrons should feel magnetic fields. And according to exact calculations, they do. If you now do Born-Oppenheimer, you freeze the nuclei and you solve for frozen nuclei how the electrons are moving, okay, in a magnetic field. And then when the nuclei start moving and they feel the magnetic field. But remember now, as the nuclei start moving, they drag electrons. So those electrons should experience the magnetic field all over again, but they can't. They can't because you already said what those states were. So you should not be surprised that Born-Oppenheimer is a disaster for molecules in magnetic fields, and it is, and that's not even me saying this. Saderbaum said this a long time ago. So you actually can do all of what I've just told you. I have no time to tell you how. You can do all that I've told you in a magnetic field as well. And so this raises all sorts of even more questions. Okay, that's all I've got. I just want to make sure I put up the picture one more time of the people who did all the work. This is not what I want to show you. I want to show you this. For the young people in the room, I'm so convinced what we're doing is right. All the evidence I say that we're doing is right. You're still getting reviews that say like this. It is not convincing that these authors understand the key element of the problem, which I say baloney, okay? You got to fight for what you believe in. And in this case, boy, I'm really hoping one day that somebody comes up to me and says, I wrote this review. Whoops. Then I'll know I've really made my impact. These are the people who really deserve all the work. Let me thank you again for the chance to speak.
Hey, I think, a fantastic talk. I'm very intrigued. So the question goes, should we all now switch to phase-space Hamiltonians, or when should we choose to do so?
Okay, so it's clear that problems of spin are going to be particularly relevant. You know, it's got to be the case that 99% of chemistry doesn't need this, okay? But now there's going to be a race, as far as I can tell, because now this is out there, right? There's going to be a race to figure out when this matters, when it doesn't matter, what are the new effects that occur. We're saying that the potential energy surface depends non-trivially on R and P. And I think there's going to be a lot of people now racing to find out when you need to do this. And then once you do that, then I think the floodgates will open because people will say, I better do it this way, not that way. Yeah, I can't tell you the answer to that yet, but we don't want to get left behind, so we are trying to race, but I think we're not the only ones anymore.
All right, very intriguing. I don't know where to start, but we could discuss this later maybe, but I sort of see the connection to what Gross sometimes tells me when he talks about the exact factorization and stuff.
Oh, sure.
But we tend to teach our students that there is one electronic potential energy surface. That's false now, you're saying. Like H2 and D2, they don't live in the same potential. And because they have different vibration, they move with different speeds,
right.
They experience different electronic potentials.
Well, I don't know about different electronic potentials, but
I mean, your phase space.
They have different dynamics. They have different masses. Sure.
Right.
Yeah.
So,
yeah.
what we teach the students about the isotopic effects, there is sort of a third effect because the potential they experience gets different. Is that right?
I don't know about the semantics of everything. Let's put this in the context of something of a way that a quantum chemist would think about this, which is to say that I'd like to. Is that Shonk?
Yeah.
You would have said a long time ago right? Here's how I would tell you, here's how I would think that you would tell your students. You would have said a long time ago that you knew up in there were going to be all sorts of static electronic correlation effects, okay?
Right.
And you would have said that down here, right? You would have said down here there were dynamic correlation effects, yeah? Good. That's just the electron-electron problem.
Uh-huh.
But if you were now to say, in terms of, let's say, surface hopping or electron nuclear dynamics, you would have also said there were big correlation effects up here. This is where surface hopping happens. You're not sure which surface you're moving on. Electron nuclear also has correlation here, right? And what I'm telling you is there's also electron nuclear correlation down here. Both of them have. And these are like this dynamic correlation, which is for the electron nuclear problem now, is still caused by all those excited states up there, only now caused by the nuclear motion, not just the electron-electron motion.
All right.
That's a way of understanding what's going on. We've been missing something for a while.
Yeah. Interesting.
Further, Philip?
Last year's Nobel Prize in Physics was given for the discovery of attosecond pulses
Yeah.
to Krauss, Lullier, and Agostini, thank you. In that community, the intriguing thing they have done so far was on an attosecond time scale, when we probe electron dynamics, nuclei stand still, everything is fine, and we can simulate what we do in experiment. And now they seem to discover that they have to include motions of nuclei. Is that related to what you're doing or saying?
Almost certainly. Yeah. I think we're going to have a lot to discover now.
Right.
I mean, it's just not obvious. It's going to be a race. So let me tell you one more thing about what Ida said. She asked about where is this going to be mattering? Where is this really going to matter? Okay. So at the end of the day now, what's going on? What's going on is that you now have surfaces in R and surfaces in P. Okay. And in general, you think they're not coupled. They should be orthogonal to each other. But now let's talk about spin. The second you put spin on there, they do couple. That's why we know spin is really going to matter. I don't know what this is going to mean for the attosecond community, but I know that the spin problem is going to be interesting. And it wouldn't surprise me if they all are. So there will be a race now. It'll be kind of fun. It's good for quantum chemistry to get shaken up once in a while, no?